Swayam Prabha. Digital India. Educated India.
So then I will introduce the next speaker. The next speaker is Mr. Alkuma Haider from Indian Institute of Technology, Patna. And he's going to present a paper entitled Stochastic Approach to Constrained Carbon Emission and Optimum Cost-Effective Planning for Indian Electricity Sectors.
Thank you, sir. Myself, Mohammad Alkama Haider, and I am from Chemical and Biochemical Department, Indian Institute of Technology, Patna. And I am very thankful to PSC and IIT Madras to give me such opportunity to present our work in this big platform. There is slight change in the title. That is, the title is Production Planning for Indian Electricity Sector with Minimizing the Cost and Carbon Emission. These are the contents of the presentation. That first we discuss about the basic introduction about the system and its uncertainty, followed by its problem statement, then mathematical formulation, followed by methodology. Then we discuss data set for Indian electricity system, followed by result and conclusion. As we know that optimal planning is always a challenging work. It is challenging because of it causes many of the uncertainties. When we planning of electricity production and demand, the main major uncertainties are resource availability and environmental conditions. So when we planning production planning and with the focus of constrained carbon emission and energy saving, it will give a sustainable option. Sustainability means that it's fulfill our present need without affecting the future needs. So the entire topic will be solved in such a manner that first we identify what is the uncertainty in the problem, and then we quantify it and convert it into a standard uncertainties and calculate the result with uncertainties. If the uncertainties are given in a probability distribution function, then we go with the stochastic approach. If it is not given, then we go with the robust approach. In robust approach, we will mainly focus Soester et al., Bental et al., and Bettismas and Sim formulation. Basically, robust optimization is a systematic procedure for optimal decision making in the context of uncertainty. The goal is to select a solution that can best handle the different realization of uncertain data. Using a budget parameter, it may regulate the degree of convertism for each restriction and it guarantee a feasible solution. It is not necessary to have a prior probability distribution function. If there is a prior probability distribution function, it is better to go with the stochastic approach rather than to the robust optimization approach. Then one of the robust optimization approach, that is Soester et al., which is given in 1973, it creates uncertainty sets in the form of boxes and employs them for reliable optimization to make sure the solution is viable. For each realization of unknown coefficient, the objective value is derived using the interval boundary values. The main drawback of this formulation is that it lost its optimality and lack of control over the level of convertism. It's basically give the worst case scenario only. Then the second formulation, that is Bental and Novisky, these formations offer a way to balance robustness with solution convertism in the context of uncertainty. It gives the model contributivity to balance optimization value and reliability level. But here is also one drawback that because it is used for the nonlinear formulation, when it goes to the nonlinear formulation, the problem size becomes so large and the guarantee of optimal solution is something like questionable. And then the third formulation, that is Bettismas and Sim, which is given in 2004. This formulation uses a budget parameter which provide a suitable trade-off between the solution robustness and maintaining optimality. The solution provide a complete span from the worst case scenario to a nominal one, and this span give the designer to make a better understanding and better decision which scenario he want to take. Either he go with the worst case scenario or he go with the nominal scenario, or in between. It is his this formation give a better choice for the designer. So in this work, we will go with the Bettismas and Sim formulation. Now the problem statement. There are n total number of generation route to satisfy the demand of a power. Like we have a nuclear power plant, we have a hydropower plant, we have a wind energy for generation of power, we have a solar energy for generation of power. So we have a n total number of generation routes, and Pi represents the production level for the ith generation. And for that generation, Di represents the predictive future demand. For each generation route, we have some emission factor which is represented by EFI, and EFI is uncertainty. Because this is a problem where we are dealing with uncertainty, we are taken three type of uncertainties. The first one is emission uncertainty, here is in this slide. The second one is operational cost uncertainty, and the third one is entire capital cost uncertainty. If we try to understand the uncertainty, let X is an uncertain quantity, and we try to express it in terms of A and B. A is a nominal value and B is a deviated value. Then A plus minus B gives the value X. In this way, the uncertainties are written here. Then the mathematical formulation. The equation 1 basically is the overall balance between the production and the demand, followed by the constraint, that is emission constraint in equation 2 and investment constraint in equation 3. And the equation 4 gives the objective function, that is to minimize the operational cost. And equation 5 to 10 are the modified equation based on the Bettismas and Sim formulation. Now this is the methodology. First, when we start the problem, we have a certain data. Then we go whether the problem is a probability distribution function type problem or a nominal one. If there is a percentage are given, we go with the robust optimization. If there is a probability distribution function, we go with the stochastic approach method. Once it is decided, then we solve the problem. Once we solve the problem, in case of robust optimization, we introduce a budget parameter. Why we are introducing a budget parameter? Because budget parameter converts the losses the it reduces the convertism. It makes the system from nominal to worst case only. So that we introduce a budget parameter, and then we check whether the solution is given a feasible solution or not. If it is not feasible, which means that we have to modify the budget parameter. If it is feasible, then we calculate the upper bound probability valuation for the assigned budget, and then we see whether the decision maker is satisfied or not, because we are planning for giving a production plan. So the decision maker decision is also valuable. So if it is not satisfied, then we change the limit. If he is satisfied, then the production plan is considered to be implemented. Now this is the data which is taken from Central Electricity Authority 2020. Here we have 6 generation route. That is one is a nuclear route, one is the wind energy route, one is the biomass, and so on. And each has a emission factor, its capital cost, the capital cost in terms of million USD per megawatt, and the operating cost. Then based on the formulations given, we have the results, and both graphs are based on the dual uncertain parameters. The one uncertain parameter is the overall cost, and the second uncertain parameter is emission factor. Like one can see that ULE is 0, ULE is 3, ULE is 6, which means that uncertain parameters in emissions are taken in the budget of 0, 3, and 6. So we have so many budget parameters because we have 3 uncertain parameters. We have 6 budget parameters. We can go to 0 to 6, where 0, 0.1, 0.2, 1, 2, and so on. So many graphs can be produced, but this is one of the result which is shown here. And the graph 2, in graph 2 we have shown 3 uncertain parameters like production cost, then we introduce the operating cost and emission cost. Now based on the budget parameter 111, this is the result, and we can see that the overall production, that is which is equal to demand, is given at the bottom. But we can see that solar the production plan have 100 gigawatt, and solar is not contributing a little bit. Only 0 is given, so is obtained. So what we do, we first try to reduce our conventional sources, and increase the renewable sources like wind, biomass, hydrocarbon, and solars are given a cap of 50 gigawatts. Earlier it was 100, now we are giving to 50 gigawatts. And coal capacity and nuclear plants are their involvement are giving downwards, and in this way we can get the result. Some results are infeasible, so there is a chance for a decision maker to get the a better result. And this is the plot based on that table. We can see that the blue line is for solar power plant, and we can find that if solar power plant is not contributing that is, it is at zero, the operating cost is around 112,100. But if it is at 80% contributing, then operating cost reduces. But one can find that for Indian scenario, if the biomass is contributing, the operating cost is going to down. So this is the complete chart that one can decide whether we have to go with the biomass or solar based on our resources available, because we have uncertain parameters. So based on our resources, we can go with these graphs. And this is the stochastic analysis approach. Then the conclusion based on the current data is that according to the result, the share of electricity by utilizing the biomass always should high to provide the energy at low cost for the Indian scenario. And cost and capital factor of energy production for solar should be improvised before it is gone to the large implementation. And with the help of applied methodology, the overall cost of the production can be determined as desired capacity of generation sources. And the robust methodology can be provide a very optimal and brief plan for electricity generation capacity as compared to the stochastic methodology. And this methodology can be applied to other areas of research business for planning purpose under a certain optimal budget. In the future work, we can also, because still there are millions tons of carbon are rising from the electricity generation. So the future work is that we have also included the carbon emission minimization in our objective. These are the references. Thank you.
Okay, thank you very much. And I'm opening the floor to questions.
No, I hear from Institute of Engineers Malaysia. Just want to have some idea about uncertainties that you mentioned.
Yes.
So how do you basically determine which is the controlling factor in order to optimize basically for this operating cost of this power supply organization?
Sir, actually in this problem, we are taking three type of uncertainties. And based on the graph, we can making the cap based on capital investment and operating cost.
So just want to just want to understand about the controlling uncertainty. I believe that out of those three, it is not always those three will be controlling. So there will be some scenario where this uncertainty A will be the controlling. Scenario 2, uncertainty B. Scenario 3 will be uncertainty C. So how do you actually evaluating on the uncertainties in order to optimize? Because we have to identify which is the controlling uncertainty in order to optimize. So there is just want to have some idea on it. So another thing on top of that, the one I commented earlier also on the reliability. So how reliable that we can make sure that whichever that listed as the optimum that really deliver at so-called any without any reliability issue. Thank you.
Sir, both of the question, there is the main theme of Betis Mass and SIM are lie on the budget of parameter. When the budget of parameters is given optimal solution based on the graph and table, we can see that because it is okay that I have shown the result on budget of parameter, all the three on the 111. But when we go for the optimal case, it can be one, it can be, because we have 5 parameters, so budget of parameter is 6. So based on that budget of parameter, we can find the optimal solution. And reliability, the term of reliability is when we, because this type of work is giving a complete span, So one can easily, the designer can take the decision whether we have to take this one or this one.
Okay, thank you very much. Are there other questions? If not, then I would like to thank you very much for
Thank
your
you, sir.
presentation. And with this, I'm also closing the session. So you have announcement or yeah. And I would like really to thank all the contributors because it was an interesting session.
So we have had long sessions since morning. Now it's time to break for lunch. The next session will start at 2. It will be on engineering energy systems.